Greetings, everyone. I hope you still are fans of trees. So I'm going to go off some of the homeworks of tree traversal, and I'm going to focus only on the tree traversal that I think is kind of the interesting one. That is the well, it's not. I shouldn't say that, but I just want to focus on one because it's not something that we will use afterwards. So. Okay, so I'm going to do number 9 is asking for the pre-order traversal, which is the same, by the way, as I pointed it out, but you can verify this, as the traversal you would get if you would put this in universal code, universal addressing. Okay, so okay, let's do this. What we do, the technique is either you break down, you trim this down, you put first the A root first, and then the 3 children, which means what? This child comes with its whole package, this comes with all baggage, and then you keep repeating the process. So that is something that we will talk about in discrete math 2. We call that the recursive definition, but we haven't talked about that. So the way that we can do it is you walk. So what you can say is the following. If I don't know whether you understand how this walk exactly works, so let me repeat this perhaps. What you do is you can think of this as walls, okay? And then you start at A and you put your left hand against the wall and you keep walking and you keep your left hand always in the wall. So that would be, you would walk this way, right? Left hand, left hand, left hand, left hand, left hand. You turn around because that's how your left hand go. You would go into the corner and then come out again like that, right? See? Okay, so you keep doing this. Basically always turning left whenever there's a turn to be made. Because sometimes you have no choice, right? Like here you have to go this way, but you always turn left. And then until you're back in this direction. And so now what we do is we just, I'll do them in orange. No, I do it in black because for some reason I have, okay, so the first one, you start with the root, that is an A, B. So the first one, you go on your path, which one you whatever you see, you write down. K, L, M. Now you go back up, you see E, but you have already E. B is already checked off, so F. That's why I color them or do something that I don't write them twice. Next comes G, I go down, N, I go around here, R and S. Then I go all the way up, mating N, G, B, A on the way, but all these are been done. So the first one, new one, is C. Then I turn around, A I've done. Then I see D, come down here, H, O. Walk all the way up, C, I. Go to D, which is already seen. Then comes J. And then it's 2 children, P and Q, and that's it. So that is the in-order list of the vertices. But as it's pointed out, this doesn't uniquely determine the tree. You also need to know of each of these, what is the degree, how many children does it have? And then in particular, you need to know which are the leaves. But that's not enough. Just to know in the leaves, even that is not enough to reconstruct the tree. There are some examples in the homeworks. I didn't assign them, but you can look them up. I just want to do very quickly, although that's not really the question here, to find a universal address. Can you find a universal address? What would be the universal address be of n? Okay, so then how do we do this? Well, here is n, right? So n will have it's the only child. So we know it will be 0.1 of its father. Okay, but we don't know what is G's address. G's address is the 3rd child of B. So he will be 0.3. So here will be G. Here comes B. So what is B? B is the 3rd child of A. So that just makes him 1, right? Because we don't write 0. The A is kind of this bit special, right? So this would be 0, this would be 1, and so on. So we know that B is 1 now. So this is the same as 1.3, and that means that the label of G is 1.3. And so the label of n is 1.3.1. Okay, what it means is you go into the first section, then you take the 3rd subsection, and you take the first other section, okay? So just given a quick application for universal addresses, because I didn't assign it, I didn't make it a special problem. So then the next one was 16a. So we had this expression x plus 2 to the cube, I don't know why they wrote it that way, times y minus 3 plus x minus 5. Okay, using a binary tree. So we're gonna, it doesn't really matter how you do this, we start unraveling it. So we start with this x plus 2, for instance. That's one of the inside, so it is always from the inside out, okay? So we have an x plus 2, we're gonna add them, since it's addition, the order doesn't really matter, so this becomes a plus. Okay, so this will take care of this box here, so this box is now done, and I can now take the cube of that box, that would be the third power, and the cube is we represent by an arrow, okay? So this takes care of, we have now this box. What else? Well, now let's start again inside. You see there are a lot of parentheses, so we go really as deep as we can go inside the parentheses. The first thing that we see is this 3 plus x. Okay, so this is separately, so I'm going to put it here, and later we will connect them when we need to connect them. So 3 plus x. Again, the order doesn't matter, but we could even maintain the order. Perhaps for some reason we want to know exactly how it was written, so we can maintain the order. This takes care of the box, but now we see a new box because now we have y minus that box. So but be careful, it is y minus, so y comes here, and then we put a minus that connects these two boxes. So now we have also this box. These are not the two boxes that have to be multiplied together, so we're going to multiply them. Okay, this is, I'll write star here for multiplication. And then finally we have to subtract 5 from this. So subtracting 5 comes in that, it's the order here is important. So this is that we get. So this is the binary tree. And so what is the prefix? So prefix, no, I only asked prefix, so I only did, yes, so A and B, sorry, A and B is set, right? Yeah, A and B. So what is B, the prefix notation? Okay, so we do the same thing again. We make our little walk. There you go this way, boom. Okay, around. So let's mark everything. I'll do it in this color now. Minus, star, plus, x, 2, 3, then I go down, I get minus, I get y, I get plus, I get 3, I get x, I go all the way up. Did I see anything new? No, 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 I finally find 5. Okay, that's, and this is what we call the prefix version of this expression. And so how would you unravel this? You see that the only thing that we can do here is what you're looking for to reconstruct it, and of course I'm not going to do it because we have it here, but the reconstruction, how would it work? You look for an inside leaf, inside vertex, sorry, with 2 leaves following it, which means, for us, means an operation followed by 2 numerical values, but either being variable or a constant. So we have, this is one occasion here, this is not, this not, this not, this not, this is, sorry, this is one. This not, is this one? No, because there's a plus here, the second one. So this definitely not. Here, this one, yes, this one we could also take together. So we can either work with this would be giving me this part, right? Or I could have done this one, which would give me this inside part. Okay, all right. So that was 16a, and then finally number 23. What are the values now? So here, there's actually, well, I did it for this particular one, but let's do it now for the ones that they give us. 23a, we have minus star 2. This is divide, so I'm going to, I rather write divide this way. 8, 4, 3. Okay. So which ones can we look for? So we're looking for an operation followed by 2 numbers. This is not the case. This is not the case. This is not the case. This is the case. This is the only one. So it is this one that we have to work out first. Now what is the value? This is 8 divided by 4, which is of course 2. So we can replace this now by minus star 2, 2, 3. I don't just replace the whole box by its value. If there are variables, of course, if there are variables, then I have to leave it as x plus 2. But here we are at, or whatever it is. So here we can write out the values, right? So what is now the next one we can do? There's only one we can do, that is this here, that is multiplication. So this stands for 2 star 2, which is 4. So this becomes minus 4 and 3. And then finally, this one becomes 4 minus 3. Be careful, right? You might say, oh, minus 4 plus 3. No, 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 no. The minus comes always in between these two numbers. So it is what is strange. So let me say perhaps one more time. What is perhaps strange is that we write it this way, but we calculate it this way. So in other words, this guy moves in between. And this is not just for this operation, it's for every operation the case. Okay? So the value is 1. Okay? B is arrow minus star 3, 3, star 4, 2, 5, star 4, 2, 5. Now you see that there are two possibilities. We can do this one, and we can do this one. No reason why we don't do them at the same time. So this is that, that is that. This is 3 times 3, which is 9. This is 4 times 2, which is 8. And this is 5. Okay? This is now our prefix notation, our formula prefix notation. So this is the only thing we can do, that is arrow. This stands for, so this one is write it here, this stands for 9 minus 8. Remember, the minus goes in between. So this actually is value 1. So this is 1, and then this is 5. So what does this stand for? Be careful. This moves in there. So it's 1 to the power 5, which of course is just 1. Okay, be very careful, right? You might think, oh, power, so it must be 5. No, no. C. I'm still doing 23. I'm looking. I hope I'm writing down the right ones. Plus, minus, arrow 3, 2, arrow 2, 3, divide 6 minus 4, 2. A couple I can do this one. I'm so sorry. Let me sneeze. I want to sneeze one more time, so be prepared. Okay. We have this one and this one. As I said, whenever you have something you can calculate it whenever you want. There are others that you cannot calculate because they have not the right arguments yet, the right nodes following, the not values following. Okay, so what is this? This is supposed to be 3 to the power 2, so this is 8. So we have plus, minus 8. This is 2 to the power 3. Remember, the symbol or the operation goes in between, right? So, oh, Professor, what are you saying? Well, guys, yeah. 3 power 2 is 9, right? The next one is 8. So we have plus, minus, 9, 8. We have division that we don't know yet. And then 6, we also copy. And then we have this one. This stands for 4 minus 2, which is, of course, 2. 2. Okay? So, yeah. So this minus is always an operation and not the negative of a number. That's why we, if you do this, well, you have to make a little bit, if you write a negative number, then the negative can be double interpretation here. So we avoid that. So let's agree that we only will use positive numbers, and if we subtract them, well, we use a minus sign. Okay? This is, of course, for instance, so it is a bit annoying to write down this guy. Because to this write down that, you have to do minus 9, 5 plus, right? And so the minus belongs to the 9. So somehow, it's the one problem you have to put then parentheses. And that is because historically we are abusing the system minus. It can mean either an operation of subtracting, but it can also just mean to take the negative. Okay, and that is the problem. That's where the confusion comes from. So, but let's stick to positive numbers. So, okay. So what else can we do? I can do this one, and I can do this one. This means 9 minus 8, so that would be 1, and this means 6 divided by 2. This would be 3, and this would be 1 plus 3, so this is 4. And then the last one, plus star plus 3 plus 3 3 plus 3. Okay. We're looking for an operation that is followed by two numbers. In this case, they're all numbers. There's only one, and that is this situation. So this is the one that we have to now resolve. So let's copy the rest. So this now, of course, this stands for 3 plus 3, which is 6. Okay, that is 6 and then 3. Okay, next. What is the next we can do? That is this one here. That's the only one that we can do. All the other operations don't have enough numbers behind them. Okay, so what does this stand for? This stands for 3 to the power 6. Okay, 3 to the power 6. Let me calculate this for you. 3 to the power 6, that is 729. So this is star plus 3 plus 3, 729, 3. So of course, yeah, here again, we're running a little bit the same problem, is that this 729 is a single number and not, so we have a little bit, when we put more space between them, then means that they're separate symbols. If they're next to each other, that means they belong to the same number, okay? Right, so what comes next? There's only one thing we can do, that is this here. That's the only operation the only box that I can unravel. Okay, this of course is addition, so we have star plus 3. We add these two numbers, that is 732, 732, and then we still have the 3. Again, we have a plus that we can work out, that is now star. This plus is 735, 3. And now we can multiply. This is 735 star times 3. So 735 times 3, that is, I don't know what is wrong with my, 735 times 3, this is 7 here. Yeah, my 7s, you might not recognize it, but this is 7, right? You hear me say it. It's 2,205. Okay, so that is how you interpret. I hope you understand how it works. And so you could also ask how. So just for the fun of it, what is this tree look like? Okay. So how do you build the tree? Well, you do basically the same. So we did first the plus 3 tree. So we have to put those guys all the way in the bottom with the plus on top. Okay. Well, the next thing we did was. This had become this 3 here. No, this has become this 6 here, right? Then we had, so we would combine a 3. I now have to do this box. This 6 was already this guy, okay? Then this is the 3 that comes to the left of it, and then this comes on top of it. This is now the parent, right? So this is now, yeah, I'm gonna write my, let me start over again, because I'm getting myself a little bit too little space, and I'm going to regret that. So we get 3 and 3, and this is a plus, okay? And that was then, I had a 3 here, yeah? And I combine them into, yeah, this is so weird that I write them underneath there. I don't know where to write them. I'll write it to the left here. I don't know. Let me write this to the left. It's binary tree, so I know that I will always go rightwards, right? Okay, so what does that do? So this is taking care of this box. And this box has now become this number here, right? So that is the number that I combine with 3 in a sum. So here is 3 and here is plus, okay? So that is that box. That box becomes this number, and then I do another plus 3. So I guess I thought I was moving left, but I'm moving right and I was moving left. So move the whole thing a little bit, give myself space. So this whole box that I just calculated is 720. No, where am I now? Sorry, this one, 732, is again with a plus 3. So again, I get the plus, and here we get 3. And then finally, this box is now starred together with the 3 that comes on this side. Right, the 3 is behind it. Not that it matters, because multiplication doesn't matter, but it is, this is a plus, right? Star. Okay, double checking that this is what I should have. Star plus 3 plus 3 3 plus 3 3 all the way back up. I'm doing my walk, right? But I don't draw it anymore. And then the 3. Yeah, that's exactly this form. So I get back the original one. Okay? All right. It was not too difficult, I hope.